Good morning, everyone. The topic of my presentation is cannabinoid system in psychiatry, and I'm moderating Dr. Shobit. Cannabis, also known as hemp, hashish, muffin, or a variety of slang terms, marijuana has been cultivated and utilized by human population for thousands of years. Cannabis preparations are obtained from the plant Cannabis sativa, whereas the other plant species are Cannabis sudralis and Cannabis indica. Cannabis sativa has been used in China, India, and the Middle East for approximately 8,000 years, primarily for its fiber and secondarily for its medicinal properties. The first described medicinal use of cannabis dates to approximately 2700 BC by the Chinese Emperor Shen, who recommended its use for a variety of ailments. At this time, the adverse properties were also apparent, and a large amount of fruits of hemp could lead to seeing devils, or a user might communicate with spirits and lighten one's body. Mitchell and Guani then reported the discovery of anandamide, a lipid produced endogenously in the brain that could activate cannabinoid receptors and function as a neurotransmitter. The endocannabinoid system comprises of mainly anandamide and 2-echinodylglycerol. Others are virodhamine, nonadine ether, N-echinodyle dopamine, homolinolol, thanolamide, docosahexaenylethanolamide, palmitolethanolamide, and oligoethanolamide. The name of anandamide was derived from the Sanskrit word anand, which means bliss. These are the structures of various endocannabinoid compounds. Biosynthesis of endocannabinoids. Arachidonic acid is utilized as a building block for synthesis of endocannabinoids and is found within the cellular phospholipids of the plasma membrane and other intracellular membranes. Synthesis of anandamide requires the sequential action of two enzymes. In the first reaction, the enzyme N-acetyl transferase transfers the arachidonic acid side chain from the phospholipid to phosphatidylethaноlamine, generating N-arachidonyl phosphatidylethaноlamine. In the second reaction, the enzyme NAPD phospholipase D converts NAP to anandamide, which is most crucial for neurotransmission. Biosynthesis of 2-echinodylglycerol requires the action of enzyme diacylglycerolipase. Endocannabinoids are not stored in synaptic vesicle for later use, but they're synthesized on demand, as is done for other gaseous neurotransmitters. An important criteria for a signaling molecule to be considered a neurotransmitter is that neuronal depolarization should lead to its release. Depolarization leads to increase in cellular calcium, which in turn promotes the synthesis of endocannabinoids and enzymes. Similar to tetrahydrocannabinol, endocannabinoids are highly lipophilic and thus poorly soluble in the cerebrospinal fluid. Endocannabinoid receptors. Cannabinoid receptors are G-protein coupled receptors and can be divided into CB1, CB2, and CB3. CB1 is mainly found in the central nervous system. CB2 is distributed in the peripheral and immune cells. And CB3 is a new novel type 3 cannabinoid receptor. In addition, they also act on type 1 vanillin receptor and peroxisome proliferative activated receptor, which have been added to the list of endocannabinoid targets activated under physiological and pathological conditions. Peroxisome proliferative activated receptors have increasing role in cognition and enhancing memory. Distribution of cannabinoid receptors. They can be found in cerebral cortex, where they have a role in decision making, cognition, and emotional behavior. In the caudate nucleus, where they have a role in learning and memory. In the putamen, where they regulate movements and influence various types of learning. In the globus pallidus, where they regulate voluntary movements. In the amygdala, where they are responsible for anxiety and stress, emotion, fear, and pain. In the hypothalamus, where they regulate body temperature, feeding, neuroendocrine function. In the hippocampus, where they're involved in memory and learning. In the substantia nigra, where they have a role in addiction and movement. And in the cerebellum, they have a role in motor control and coordination. And in the dorsal vagus complex, they are involved for emesis. Neurotransmission. The cannabinoid receptor is associated with G proteins that mediates its intracellular signaling by inhibition of adenyl cyclase, which leads to decrease in the levels of CAP. Activation of CB1 receptor also leads to activation of potassium channels and inhibition of N-type calcium channels. As calcium is integral to neurotransmitter release, cannabinoids can block neurotransmission through this mechanism. Inhibition of cannabinoids block the release of GABA, norepinephrine, and acetylcholine. Inhibition of norepinephrine and acetylcholine produce an overall inhibitory, and inhibition of GABA produces an overall excitatory effect. Cannabinoids also appear to increase the release of brain endorphin neurotransmitter and increase dopamine release in the nucleus accumbens, which is a reward center relevant to addiction and retrograde transmission regulated by endocannabinoids. During development, the enzymes responsible for cannabinoid synthesis are expressed both in the pre- and postsynaptic neurons. However, in adult brain, synthesis of endocannabinoids appear to be predominantly in the postsynaptic neuron. The second neuron can release endocannabinoid that diffuses across the synaptic cleft and inhibits further neurotransmitter release from the presynaptic neuron. This diagram shows retrograde neurotransmission, where the enzyme is released from the postsynaptic neuron and inhibits the presynaptic release of endocannabinoids. As explained earlier, so in the first, it shows the normal anterograde neurotransmission, and in the second diagram, it shows retrograde neurotransmission, where endocannabinoids are released from the postsynaptic neuron and they bind to the presynaptic neuron and inhibit its release. As explained earlier, NAP is generated when N-acetyl transfers the arachidonic acid side chain to phosphatidylethanolamine, generating NAP, and further anandamide, and similarly generation of 2-arachidiol glycerol. Now they are inactivated. Anandamide is acted upon by fatty acid amide hydrolase, generating arachidonic acid and ethanolamide, and 2-arachidiol glycerol is inactivated by the action of the enzyme monosylglycerolide. Physiology of cannabinoid receptors. CB1 and CB2 decrease adenyl cyclase, increase focal adhesion kinases, and promote the opening of potassium channels. GPR55, also known as cannabinoid receptor 3, increase intracellular calcium. TRPV1, type 1 amyloid receptor, increases intracellular calcium, increases caspases, cytochrome C release, mitochondrial tackling, and fluorotropic kinase. And PPRs increase reactive oxygen species and tyrosine kinases and adiponectin. Neurobiological basis. Cannabinoid receptors in schizophrenia. Heavy use of cannabis can produce psychotic symptoms in individuals with no prior history of psychiatric disorder, though it is unclear whether it is solely due to the drug or an underlying vulnerability to psychosis in such persons. Cannabis use often worsens psychosis in schizophrenia, and heavy use has been associated with developing schizophrenia. Nonetheless, the endocannabinoid system has implications for the pathophysiology of schizophrenia, as cannabinoid signaling appears to increase the release of dopamine. It is also known that schizophrenia is associated with brain abnormalities induced during the development of CNS. A number of findings suggest the pro-neurogenic role of CB2 receptor in the control of fundamental neural cell processes. Therefore, it can be hypothesized that the lack of CB2 receptor might impair neural development, thus indicating relevant alteration in several brain areas. There has been a study which showed that clinical remission of schizophrenia has been reported to be accompanied by significant decrease in anandamide and CB2 receptor mRNA levels in the peripheral blood mononuclear cells, whereas a contrasting study showed that a diminished CB2 receptor function and is associated with increased susceptibility to develop schizophrenia. This diagram shows the temporal relationship between exposure